Yeah, so yeah, I'm going to talk about how do we play with the relations in the group to achieve certain properties. So we all know that if we write a group in this presentation in the classical way of generators and relations, we have a lot of freedom. We can choose the way to do that. So I mean, even like the most naive group, right? If we take Z cross Z, we can either write, you know, AB and then the commutator, so like BA equals AB. But of course we can, you know, we just do a silly thing and we add another generator maybe, and then we can say something like maybe AB equals C. So ABC inverse is 1 and BA C inverse is 1. And this is, I mean, it's going to be just the same group. So it's just this, you know, combinatoric game with the letters. And what I'm going to talk about today is a few questions which we're able to answer. And this is a joint work. Most of it is joint with Barry Greenfeld. And some of it is also joined with Alexander Oleshonsky. So using this kind of games in small cancellation or small cancellation inspired methods, which I'll talk about a little bit, we were able to construct weird groups answering various questions related to the topology and the measure and the structure of groups. So 3 specific questions I'm going to talk about their solutions. So the first one is something related to identities that hold in groups with high probability. With high probability. So the picture to keep in mind for this question is something like we have a group G and we have some property which holds, you know, almost everywhere. And I will say what's almost everywhere because it's not necessarily a compact group. Maybe it's like a large group, but still we can somehow formalize. It's actually a bit similar to what Sasha did today. So like something which holds in many places on the group, and we wonder like, what does it mean about the entire group? Does it mean anything about the entire group? And here I will talk about solutions for a few questions posted by Gidi Amir, Guy Blachar, Maria Gerasimova, and Gadi Kozma. And I think I was very excited about this one, so I did give a few talks about that, so I apologize if you already heard me talking about that. This will be the first part. The second question I'll talk about is related to Zariski topologies on groups. Topologies on groups. So, and the picture to keep in mind in this case, and this is something Yves Cornelier taught me when I was in the master, like what is the Zariski topology on R? So you may know that it's the topology generated by non-zeros of polynomials. So if you have like a polynomial, maybe x minus 3, x minus 4, the zeros are 3 and 4. So the open set related to this polynomial, associated to this polynomial, would be just like the entire interval minus these 2 points. And this gives if you take as a basis all polynomials, then we get a topology on R, and one can, in an analogous way, can define a topology on a group by stating that open sets are non-vanishing sets, the sets of that don't vanish on certain polynomials on the group, and this gives a topology on a group. It has similar property to this topology, so it's like not Hausdorff, so but it is a topology on a group. I'll talk about this, and we'll answer a question by this a long list, so let me not get confused. So by Elliott, Jonusas, Mesyan, Mitchell, Morayne, and Peresse. And lastly, I'm going to talk about, and this one is very recent. We still didn't write it down. It's like, so I'm going to talk about groups containing no free semigroups. And here, when I say free semigroups, I mean free non-abelian semigroups. So you're probably familiar with the question like, does a group contain or not contain a copy of F2? That's very, I mean, we care about it a lot, right? We compare it with amenability and stuff like that. But also, I mean, this property of containing or not containing a free semigroup, I mean, it also tells us a lot about the growth, about the structure of the group. So, and it was suggested by, okay, I'll talk about it more. I'm going to talk about an answer to the question by Longobardi, Maj, and Remtula. So this is the same Remtula from, I think, Yair Glasner's talk. So they have a theorem about characterizing which solvable groups have this property, so that they contain no free semigroup, and they said they have a suggestion what can be the family of all groups not necessarily solvable, on groups in general containing no free semigroup, and so we answer this one. Okay, so that's what I'm gonna talk about. Oh, and the picture maybe to keep in mind here is something like, I mean, F2, but yeah, just the positive half of this, and you know whether this part lives or not inside your group. Okay, and on so it can be defined on groups. It can be defined on semigroups. I mean, you have in mind like algebraic groups, or
on R, if you take the additive structure, you can write multiplication, and you wrote multiplication.
Yeah, so you are right. So what I mean, so on a group, I will consider like what is a polynomial on the group for me. So it's something looking like A1 is let's call it G1 because it's an element of the group. Maybe X, G2 maybe X to the X cubed, G3 maybe X to the minus 5, G4. This is a polynomial, and this may and I can say this equals to E, and this defines me a set of points, and these will be like the zeros of this polynomial. So all X in G which satisfy this will be like the zeros of this polynomial. So this will be a closed subset, and then with this I generate a whole topology on the group. Yeah.
What you wrote there as an example is of that point.
What I wrote here was like all x's. I meant like the set of all x's such that this is not zero. This is an open set in the Zariski topology. Yeah, it's you're right. It's like it's not the same definition, but it's like I mean inspired. Yeah, people I think that kind of like invented this topology on groups inspired by like the Zariski topology on. But maybe maybe the name Zariski topology is a bit misleading because if we take an algebraic group, and we take the Zariski topology on the field, it's not going to be the same as if we take the Zariski topology on the group. Yeah, you're right. So it's maybe not the perfect name, but that's how it's usually referred to. Okay, and please ask me a lot of questions, inspired by Anush. Yeah. Okay, so.
When you say equal E, you mean not equal E and things like that?
If it's not equal E, this would be like the open sets. Yeah, thank you. Yeah, right. The non-vanishing of a polynomial. And and one also does it for semigroups where you only let positive powers there. Yeah, you take all the, yeah, right, this is like the, yeah, sub-basis, right, yeah, all intersections and unions of such sets. Yeah, okay, so let me, oh wait, I learned how to do that. But let me start with one and then goes there. So I'm going to talk a little bit about identities that hold in groups with very high probability. And somehow this entire thing begins with a very cool classical theorem from the 70s by Gustafsson. It's sometimes called the 5/8 theorem. And so this is a theorem by Gustafsson. And it says the following. If you take any finite group, and suppose that the probability that two group elements commute, so let me do one instead of e. So the probability that two group elements commute, if this one is at least 5/8, then your group already must be a billion. Okay, let me do the if here. So if this probability is more than 5/8, then the group G is a billion. So, and what is the probability here? So it's a finite group. So I just sample a random element, I sample another random element, I take the commutator, I check whether they commute or not, and I count what's the probability it holds. So it's a very surprising thing, I think, because it's like it means that you cannot be very abelian, like you cannot be 90% abelian. You can, like, the most abelian you can get is 5/8 abelian. That's the most abelian a group can get. And the proof for that is so elementary that you can show it in second year undergraduate course. It's like 2 lines and very, very nice and elegant, just using indices of subgroups. So we have this, and actually, I mean, motivated by that, there were many analogs proven of the same form, but just instead of saying like commuting, we say something else. So if a group is satisfy nilpotency law with high probability, it must be nilpotent. If it satisfies the metabelian law with high probability, it must be metabelian. So there are very nice results of this spirit. I will not write, but I'll say names of a few people that did this type of stuff, also for power laws: Lafay, Mann, Martinez, Delizia, Jezernik, Moravec, and Nicotera. And so this, you can think of this as like any identity. This is also sometimes called like a group law. So if a group law holds with high probability, it must hold in full. But there are no general results. Like people don't say something like any law if it holds in high probability. But like for each specific law, you can go and look if there is like a critical threshold above which you cannot get. But I mean, somehow this is about finite groups, and I think most of us, which are like in a measure perspective, we don't care about finite groups. But so the question is, how is this relevant to infinite groups? And in recent years, there were really cool modifications of this concept of a probability gap to infinite groups. So how do we, I mean, if we have an infinite group, how do we estimate? What does it mean to commute with high probability? There is no probability measure on the group, obviously. So there are two conventions. So so what about infinite groups? So I set in the back, and therefore I know that you don't see well the bottom of the board. Okay, so what about infinite groups? So in infinite groups, we basically, in certain cases, you know, if it's amenable, for example, one can approximate it by Fellner sets and then maybe take the uniform distribution or sample an element from a Fellner set, so people do that. But if the group is just, I mean, any finitely generated group, there are two methods how to two common methods how to sample elements. And one would be just looking at the Cayley graph. So if we look at the Cayley graph of our group, maybe we can do the following. So maybe, you know, we choose an element, we take a random element at the 0 ball. OK, that's E. Does it commute with E? Yeah, it does. OK. We choose a random element at the 1 ball, and we choose two independently random elements from the 1 ball. We check, do they commute? We get some number. What's the probability that they commute? And then we keep going. We choose like two independently random elements at a large ball, and we check what's the probability they commute. And we get, you know, many numbers, and we see what happens in the limit. So we kind of like, you know, imagine that we take like a huge ball in the Cayley graph. We exhaust the entire group like that, and we ask if we take two random elements, what's the probability that these two elements commute? And now we wanna check, or like the question we can ask is, suppose this probability is high. So suppose that, you know, the commuting probability is very high. The group is like very commutative. Is it a billion? So we play the same game, but now on the infinite picture. Like, but we have the same kind of like moon shape of like, if it looks a billion, so it's like, you know, it walks like a duck and it swims like a duck. Maybe it's actually, it's actually a billion. So that's a question. I mean, this is only one way. So let me tell another way, which may sound to you more sophisticated, but I mean, and this would be, instead of just like looking at the Cayley graph, okay, again, you look at the Cayley graph, but you take a random walk, and you let this random walk, and you let it walk, I don't know, like 5 steps, so it gets somewhere. And then according to the distribution of this random walk, again, you can sample, you let 2 of these guys walk, and then you take 2 independent points in the group sampled by these random walks, and you check what's the probability that they commute. And again, you get a number in the limit when the so this is I think similar to such as the definition of like a topologically mixing, right? Of like we just look what happens in the limit of this, like moving this or using this like randomly sampled elements. Okay, and again we consider what's the probability that things commute, or like that elements satisfy something after a long walk. Okay, so we have these methods. I mean, they may work or not, and I think a very beautiful theorem from like 5 years ago is by Toynton. And what Toynton shows is that exactly the same 5/8 theorem holds if we sample the group using random walk. So the theorem says that let mu, okay, so it's like mu convolved with n is like the n step. So like this is my random walk, be a random walk, and it can be any random walk as long as the support is symmetric. And of course, generating, because we want to see the entire group, so we don't want the walk to just go along a subgroup. So symmetric, and it's called non-degenerate. So the support is generating, non-degenerate. So any such random walk we take, if the probability you see of commuting elements, if this one is larger than 5/8, not even in the limit, but just even if in the lim sup. So even if sometimes it's larger than 5/8, and this here the limit is so this is the probability that this happens, and the probability is taken on the nth step of the random walk. So if by any random walk you pass this threshold of 5/8, then the group already must be a billion. Of 2 independent copies. So how should do I say this cross this? Right. So this is independent random walks. So the group is already abelian. And I think it's notable that this does not depend on the random walk. I mean, any random walk you would do, still you get the same threshold. So like that's actually like the right number. This is like the gap for, we say this is, we call it the probability gap for the commutator law.
Without the limit soup, is it clear that the limit exists?
Oh, it's not at all clear that the limit exists, and that's one of the questions I'm gonna address. Yeah, it's a good question. So lim sup is kind of like a very weak assumption. Some theorems also, I mean, state things about like the lim inf, which is, I mean, maybe a more common setting. So at least like if there is a limit, it's above. Yeah. For infinite groups, I think what you can do to make, so for finite groups, it is sharp, and an example is the dihedral D8. So for infinite groups, I didn't think of the details, but I guess what you can do is like maybe multiply D8 by something which is, I believe so, but I mean, I don't have an example in mind. I guess if you play with this D8 and multiply it by, huh? D8 by D8 times Z, but then I mean, does it? I mean, will it still have the same volume? I kind of like need to. Yeah, okay, I trust you on that. Okay, so D8 times Z. Go ask Josh if it's wrong. Yeah. I think yeah. In the beginning, I was like D8, but which 5 elements commute? But then I realized it's not. Yeah, it's not 5 elements. It's like there are 64 pairs, and like out of these 64 pairs, there is exactly 5/8 of the pairs of the elements of D8 that commute with one another. Just I'm saying something which confused me, and maybe also, so maybe it's also confusing for you. Okay. Yeah. So it should be sharp. So this is this beautiful theorem by Toynton that the way I read it is like, okay, these ways, these methods actually work. I mean, it's actually possible to do this on infinite groups, which is a priori not obvious. I mean, that this concept actually even makes sense for infinite groups. But this theorem is kind of a good evidence that it does make sense for infinite groups. And there are, again, few other theorems on this spirit proving, oh, by the way, for Toynton's result, there is also a second part that, in fact, even if the lim sup is just positive, so if this same lim sup, so I've been told that I can just push it up there. So let's, okay. So even if I take here, if I take this lim sup, and even if it's just positive, it doesn't need to, I mean, get to 5/8. But even if it's just positive, then the group is already virtually, then G is already virtually abelian. And there are more results in this spirit, and I want to just mention one of them, or maybe two, which is about power laws. So Amir, so these 4 authors I was referring to, Amir, Blachar, Gerasimova, and Kozma, proved a few theorems about probability gaps. So Amir, Blachar, Gerasimova, and Kozma proved a few theorems about probability gaps of this type. So for example, they showed that if the probability that x squared is equal 1, so x has order 2, if this probability, if the lim sup is positive, if the lim sup of this probability, and again, it's the same setting, so like whatever random walk, symmetric, non-degenerate, if this is positive, then the group is already, then G is virtually abelian. And this, I believe, was confirming like a conjecture by Michael de la Salle. Is this correct? Right? And Lehman, right? And they have another theorem saying that if the lim inf of the probability that x cubed is 1 is positive, I think, no, it's not positive. It surpasses some gap. Then this. So let's say I don't remember what's the gap, but if it passes some gap, then this holds in G as a whole group. So G satisfies this law. So for all elements, if it holds for most elements, it holds for all elements. Okay. Now I will call this word, which is okay. And following these results, A, B, G, and K raised a sequence of questions regarding the validity of this sampling method. So we think of it as like a way to sample the group. A way to sample the group. And we can ask, like, how good is this way? Does it actually work? So they had like 6 or 7 questions, but let me write a few of them. So one is the question whether this limit even needs to exist. So does this limit exists for every law? So which means for every word W? And if it exists and it's high, does it mean that this actually holds in G? Like if I see some phenomena which holds with very high probability, does it actually need to hold? So suppose, and let's take the most extreme case. Let's say that the limit is actually 1. So suppose that I have that the lim sup of some phenomena that I see, of some identity. Let's suppose that the lim sup, and one can ask also about the lim inf, suppose that the lim sup is actually 1. Does it mean that this identity actually holds in G? So it's satisfied by all elements if it is satisfied by many. They also ask specifically about power laws. So they ask, is it true that if I have that the limit of the probability of x to the n equals 1 for some n, if it's 1, or the question is, does all, or let me phrase it like that, does all power laws have gaps, have probability gaps, or do all power laws, so these identities of the form x to the n, do all power laws have probability gaps, so this phenomena? And another very important question is maybe something which should make us uncomfortable, is that this definition depends on the Cayley graph, like the definition, the way we define this probability depends maybe on the generating set we chose, because different Cayley graphs may lead to different limits, or maybe on the random walk we chose. So the question is, like, how strong is the dependent? Does the limit depend on the generating set or on the random walk? Okay, depend is with E maybe? I don't know. Okay, so this is kind of like, all these questions are by Amir, Blachar, Gerasimova, and Kozma.
So not only whether the size of the limit gap depends on the generating set, but even possibly the limit doesn't depend?
So in fact, they posed this question, and they even proved that the value may change. So they constructed an example in which 2 different generating sets give you different numbers, but both numbers were not 0 and not 1. And then, I mean, it's exactly your question. Like they were asking, like, okay, maybe the number changes from, I don't know, 3 over 5 to 4 over whatever 9. But I mean, is it essentially depend in the sense that so let me refine this. So they ask, is it possible to get, for example, 0 with respect to one generating set and non-zero with respect to another? Or same, you can ask with 1. In fact, we show that you can even get 0 with respect to one generating set and 1 with respect to another. So I mean, it's so answer is strongly depends. But you are right that like it's like actually two questions here. Like does the value depend, and does the value 0, 1 thingy depend? And also for the existence, right? Like you can ask, like, does there always, for any generating set, it stays away from 1, or like is there a strict number like this 5 over 8 which always appears, right? Right. Yeah, I wrote you an abbreviated version of all these questions. Each is more like a paragraph. No. It just needs to be non-degenerate. Yeah.
It's not even finitely supported.
So here it is. I think for Toynton, maybe I forgot to write this. Maybe for Toynton's and for their theorem also, they do assume finite support. For our theorems, we definitely assume finite support of the measure. I need to check that. I don't remember. Actually, yeah. Sorry. Okay, and so I'm gonna now, like, instead of I will not like write the full statements of the theorems, but I will just like put a picture of like the results for these questions. And actually, I mean, so for us, like, the breakthrough was to figure out this one, and I'll draw a picture of this. So kind of like, I mean, I think that what we originally thought is that, yes, if something looks like, if not, even if you assume here lim-inf. So if you send a random walk, or if you look at the Cayley graph and you see that something holds everywhere, I mean, you would thought it actually holds in the group. And I think that for us, the critical moment in this work, and this is a joint with Barry Greenfeld, was to figure out that we can construct a group. We construct a group G, which is finitely generated, such that the following holds. So whatever random walk, and it doesn't even need to be symmetric, whatever finitely supported, so for every finitely supported random walk, for every finitely supported non-degenerate, of course, so it needs to see the entire group, finitely supported non-degenerate random walk on G, when you look at the probability that some power law exists, and so we fix n, so there exists G finitely generated, and some very, 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 very large n, suppose like maybe more than 10 to the 10, the probability that a random element that you choose has order n is 1 in the limit. The limit actually exists, and it gives you 1. So this is when the random walk tends to infinity. So let's not call it K. And same holds in the Cayley graph. So also, let me just say, also in the Cayley graph, if you sample large balls, you still see only elements of finite order. However, G contains a free group. So G contains a copy of F2. So it's like very, very, very non-torsion group. Like it has a free group in it. And actually this says not only that it does not satisfy this identity, but it doesn't satisfy any identity because it has a free subgroup. So kind of this is to say that if we look at this group, even if we know that wherever we go, we will always see only elements satisfying something, it may not be a duck. Like it may be something completely different. Like it may be a very interesting group. So we think of it as, I mean, there is somehow hidden, very narrow here, a copy of F2, which cannot be tracked by any random walk. So the random walk does not need to be balanced in the sense that, I mean, you can take a random walk which is supported mainly with very high probability on this copy of F2. Still, I mean, eventually you will not see this copy of F2. You will only see with probability 1 elements of finite order, of this fixed finite order. And somehow, after we figured out this, we started like manipulating this construction to give like negative answers to all the other questions. So the picture to have in mind is like, does all power laws have probability gap? So no, we have like a picture of like a group such that the entire group satisfy this, but still it has like a small copy of F2.
What is the condition that it's essentially large? Or?
It just needs to actually, because we use some tools from Oleshansky's small cancellation theory. So actually, we assume that K is odd and large enough. But since Oleshansky's work was already extended also to even Ks and not as large, so I think, I mean, such construction should also be possible for even K and maybe not as large as we assume. But I mean, since the question was just like, you know, is it always the case? So I mean, if it's not always the case, that's, I mean, good enough for us. So I don't know to tell you for sure. So in our assumption, yeah, K is very, very large and even, and odd, sorry. Yeah.
Do you have explicit values on K?
Yeah, so the explicit value, so we use a lot of lemmas by Oleshansky's, and his explicit value is at least 10 to the 10. So this for sure works. That's definitely not optimal. I mean, yeah, there is since then like a, you know, a whole industry of making the constant lower and lower. So probably any constant which works for the Berenside group's construction also is good in this case. Yeah, but for us the value is at least 10 to the 10. Yeah, actually for little k's, I mean, it can be proved that there is a gap, right? Like 2 and 3, these are works of Amir, Blachar, Gerasimova, and Kozma. That if you are very much order like 3 torsion, then I mean you are 3 torsion, and probably it's like that also for other small values. Okay, so yeah, so after that we kind of like, you know, we started like playing with examples, and to understand, does the limit always exist? So we were able to construct a group, and this is also, so the next theorems are also joint both with Berry and with Alexander Oleshansky. So we constructed groups such that not only that the limit does not exist, but such that, so another group such that the set of partial limits, so the set of partial limits of this probability that we measure. So if we measure, what's the probability, if you sample a random element, what's the probability it has order k? So the set of partial limits is the entire interval. So it's like, the way to think about it is you have a group. If you look at a large ball in the group, it seems to you as if all elements have finite order. If you look at even larger ball in the group, it seems to you like no elements have finite order. And if you keep going and you look at the even larger ball in the group, it seems again like if all elements have finite order and so on. So like you keep oscillating between these two. So like the limit definitely does not need to exist. It may oscillate as much as you want. And also for the dependence of the set of generators. So the picture is like we construct a group such that with one random walk, if you sample elements, so both, we have two random walks, both are generating, both are non-degenerate. With one random walk, if you take it, you with probability 1 hit an element of finite order. And with so this is a random walk supported on T, and you have another generating set S. If you go along the random walk generating by S, supported on S, you always hit an element of infinite order. With probability 1 in the limit, you hit an element of infinite order. So it means that it's very, very sensitive to manipulations of generating sets. Yeah. So and all these last three theorems are joined with Greenfeld and Olshansky. Yeah. So I think so I think maybe like the takeoff from that is that like yeah, this method, this sampling method is still has still needs a lot of it needs to be restated in the sense that like taking the limit as is like with respect to some random walk, it still does not predict well enough the properties of the group, or it may not predict well enough the properties of the group. Yeah. Okay, and I told you it's all done by manipulating group relations. So somehow the trick is so we put some generators, maybe like A, B, and then many other, but finitely many generators. And so this is an infinitely presented group. So we add infinitely many relations, but we add them one by one. And whenever we add a relation, we make sure it is so long and so different from any other relation we already added, such that at every finite step, we have a hyperbolic group, and this is kind of like a result of this, like if your relations are very, very long and very different from one another, so kind of like your isoperimetric inequality comes out to be like with a lot of boundary to a little volume, and it makes the analysis of the analysis possible and even easy because kind of like it's so hyperbolic that it's somehow similar to the free group, and then we can kind of like control where the random walks go in a way. Okay. This is about like the identities in groups, and yeah, are there questions about that? Because otherwise I'll go to the Zariski topology thingy. Yeah. Finitely generated, infinitely presented. Yeah, it's not that the group in the end is not going to be hyperbolic, but like whenever, so at any finite step, your random walk will kind of like only see certain amount of relations in a sense. So like at any finite time, you can think of it, you can kind of imagine that you stopped adding relations at some point, and then you kind of pretend you're the group is the limit of these. It's a Binamini-Schramm limit. I mean, it's actually like the Cayley graphs are limits of the groups with only finitely many relations added. Yeah.
In the case of the power law, you need to add more relations than just powers.
We add only powers. But the way you add powers need to be very specific. Like you need to, like the kind of like what you need to decide is which powers you add. Yeah, so you are right. It's a very, straight to the point question that like all the relations we add would be of the form some word, some I don't know, A, B, X1, B, X2, to this very large power, maybe like 10 to the 10, and always the same one. So we add this, and then we had another long word to the 10 to the 10 equals 1, and so on. So these are very long relations. But kind of like the secret is hidden in like which words you take. And when you pick the words, you want them to be different enough than what you already chose. So you want to like a very minimal set. Like you don't want to. So at any step, kind of like you want to know which words you already killed. You already made them finite order. And then be very careful about like how many and what's the next words you're going to kill. You're going to like make finite order to make sure that the random walk sees enough words of finite order, but without killing the free group. Yeah.
Does it say that the random walk in the hyperbolic group tends to see only the words which are kind of the small constellation words?
So what you can say, I think, is that if you walk on a hyperbolic group, and you got somewhere, you know that there are not too many ways to get there. So if you are like in Z2, and your random walk got, and here you have some element, maybe it has a whatever property. There are many ways to get there, like, like this, and yeah, various ways. In hyperbolic groups, it's not like, usually, like, if you hit a point, there is a good reason for that. Like, you probably think about the free group. If you got somewhere, it's because you actually went there, intentionally. So kind of like in these groups, it will be the same because they are so hyperbolic. Like the circles, it looks like a free group, like a tree. The Cayley graph looks like a tree, apart from some huge cycles, which are these relations. And they are so huge that when you walk, you hardly see them. So basically, it feels like if you're walking on the free group. So you always can, if you got somewhere, you know what the probability you got there, because you can track what's the way you did to get there. There are not like too many options. That's kind of like the way hyperbolicity is used. Okay. Okay, so let me talk about a little bit about the Zariski topologies on groups. Oh, actually, if I yeah, so the Zariski topology can be defined on any group, and it is defined by claiming that the sets of points which do not vanish on certain polynomials are open. So if you want something more formal, so you can consider like polynomials on the group. So let G be a group. And polynomials would be elements in, so let's say polynomials in G would be elements on like the free product of the group with the subgroup generated by some variable x. So these are elements like, some element from the group, x to some power, some element from the group, x to some other power, some element from the group, and so on. Okay, so this is a polynomial, and the topology is generated by open sets, which look like that. So these are all the points x, such that some polynomial, maybe qx, is not 1. So these are the open sets, and qx is some polynomial. Okay, and I told you that, so this is the Zariski topology. It is usually denoted by the Zariski topology of the group G. And similarly, one can, if G is a semigroup, one also defines same game for a semigroup. So if F is a semigroup, if F is S is a semigroup, then one can also define the set of polynomials on a semigroup. So this would be, a constant from the semigroup, and again, some variable. But now the variable must be like with positive power, because we cannot take negative powers in a semigroup. So, for example, it will look something like, maybe some G1 x cubed, G2 x squared, G3. And again, we claim that the open sets are non-vanishing of polynomials here. And here, when we'll say non-vanishing, we will do like qx is not the same as px to allow more flexibility. This would be a positive polynomial, so like a polynomial in the semigroup, and this would be a polynomial in the semigroup. And we claim, so in groups you could also write the same, but then you could take the polynomial here and move it to the left-hand side. Okay, and this gives the topology, and and you know how it is with topologies. Like sometimes, like you know what the open sets are, but then, I mean, you know what the basic open sets are, but then it's kind of like difficult to understand what sets will be open eventually, because right, you have the intersections and the unions, and you know, if you think of R2, like the topology generated by open circles is the same as the topology generated by open squares, right? Like it may end up being the same, and so the question here, and this is the question asked by these like 7 authors, which were like playing with this with these topologies, is if I consider a group G, so you know, if you have a group, it's both a group and it's a semi-group also. So you consider on the group, you can put on the group the Zariski topology, so as a group, and you can consider the positive Zariski topology. So this is the topology on G as when you think of G as a semi-group. So you have slightly less open sets because you are only allowed positive polynomials. But in all known examples, these two topologies coincide. So consider a group G. Is it true that the Zariski topology on G is the same as the positive Zariski topology on G? I mean, do this? So for all groups for which these topologies are well understood, the answer is okay. So the answer is not. So let me say yes. For abelian groups, it is known that it is the case. It is also known for, for if you have a finite exponent group, so this is kind of, if you have a group with finite exponents, so like all elements have order at most 10, then, I mean, x inverse would just be like x to the 9. So, I mean, you could recover all polynomials, all polynomials by only positive polynomials, so it's obviously that the answer would be yes. And also for the free group, the answer is yes, and this is like a more of a difficult result. This is a long paper by by Chiswell and Remeslenikov. Okay, so for all known example, this is known to be the case, and the question was, is it always the case? And okay, and again, kind of like it's the same. It sounds like we're party poopers, but like it's really like again it's the same tools that are used to build kind of a strained construction using I mean, a certain choice of relations. So the theorem, and this is joint with Berry, is that the answer is no in general. So we can construct a group on which the positive Zariski topology is different than the actual Zariski topology. So this is to say that these are not necessarily the same. So maybe I'll just say the answer is no, and this is yeah, by construction, I want to say. Okay, yeah, I was not very well planned with the time. I was yesterday. The day before yesterday, I tried to like do all the lecture like from the beginning to the end to see it actually fits in 55 minutes. And then I mean, baby Adi was like not going to sleep, and I was like, I mean, walking with her, and then I was like shaking her, and then I like remembered that like you can, if you shake them very strongly, like it doesn't. There are no signs of violence, but like they understand the hint. So I was like, shaking her like that, and then she started like laughing. And I was like, okay, I'll just like give up. Yeah, so I didn't time it. Okay, so no. So answer is no. Yeah, but she's okay. Yeah, no worries. Now I know how to make her laugh. I mean, it's actually a good thing that I found out how to do that. but okay, so what will I say for conclusion? I will just say that maybe next time we'll meet, I'll talk about this, because this is like very, I mean, very, we still didn't write this one down. But maybe I will just say that kind of, so an obvious class of groups containing no free semigroups is the class of nilpotent by finite. We know that, okay, we know that nilpotent groups cannot contain free semigroups because, I mean, because of growth considerations. Like if you contain a free semigroup, you have a good growth, and nilpotent groups don't have that. And if you do nilpotent by finite, it doesn't change this by much. And it turns out, and this is a result of Shalev, that, I mean, you can also be more flexible. So you can, so still, even if you go not nilpotent but locally nilpotent, and not by finite but by torsion, still, I mean, it's fine, and you contain no free semigroup. But Shalev and Semper have like a result saying that if up to elementary equivalence you don't contain any free semigroups, you must be in this framework. So you must be nilpotent by torsion, locally nilpotent by torsion. And the question these authors ask is it true that this is a characterization for the groups containing no free semigroups? And again, I mean, we play this game with relations to construct a group which is not of this characterization they suggest, but still contains no free semigroup. So again, it's like by, we add some relations to kill whatever potential semigroup is going to raise there, and like, kill it by closing some cycles, but do it gently such that it does not destroy the other properties. Yeah, okay, thank you.
Thank you for your talk. So are there questions? Yep.
Yeah. Two questions. One, re3. Sorry, can you clarify the question again? Because, like you said, groups
yeah, I'll write the.
Like, well, I'm trying to understand why the Grigorchuk group is not something I should be worried about here.
The Grigorchuk group is torsion, so it is in the. So the question is, suppose suppose G contains no free, and free I mean non-abelian free, like at least two generated, free semigroup. Is G necessarily locally nilpotent? Locally nilpotent means like any finitely generated subgroup is nilpotent. Locally nilpotent by periodic, so by torsion. Yeah, by a group whose all of its elements have finite order. Yeah, this is the question. And they are not locally. So I mean, if it's possible that I don't know that, and it's like was already. I mean, this already solves it. I mean, it's possible. If so, I mean, you saved me from writing this down, like the entire paper, which is kind of like still on Scratch. So you're saying so you're suggesting that the Grigorchuk. Oh, I don't know how to spell Grigorchuk.
Like there are known torsion-free groups that do so.
Torsion-free groups which are not locally, and you know for sure that they are not locally nilpotent by torsion. I mean, you can, yeah. I don't know which groups, and I don't know their property.
Are torsion-free, so they don't have torsion subgroups.
It doesn't mean the torsion subgroup. It means so here I mean that it has like a large, so it has a large locally nilpotent. So it has a locally nilpotent subgroup, N in G. So N is locally nilpotent. And the quotient and G mod N is torsion. Are like that? So it's possible. So if so, I mean, so I put this like 3 minutes onto that. So to find out that like we don't need to write this. So okay. So you're saying they are like that. They're not like okay. I mean so okay. So you did save me a lot of time.
I'm
so,
saying that they are not a counterexample.
oh, they are not a counterexample. And so they are not of this type. So they are not a counterexample. I honestly don't know. Yeah, I don't know how to answer your question.